Chapter 23, we're going to look at sample environmental indicators and standards. So these are environmental indicators that we could use in field work and in sampling the environment. These ones are specific to freshwater systems like a river or a lake, and we're going to use a lot of these when we were going to go to the Mitchell River, which hopefully we'll get time to do. The first one we're going to look up, these are all physical and chemical environmental indicators. So they're physical and chemical that we're looking at. Okay. So physical and chemical environmental indicators. The first one is turbidity. Turbidity is the measure of suspended particles or solids that are in the water. They can block sunlight from reaching the submerged plants. They can cause dissolved oxygen levels to drop, which we'll talk about later. And it can be a whole range of things that they do. So it's a measure of fine particles suspended in the water column. It gives the water a cloudy appearance. The turbidity of a water body is important because it influences the amount of light that gets through the water and penetrates the water. So if you have more turbidity, you get less sunlight going through the water, which means you have less plant growth that can occur, which means less photosynthesis, which means less oxygen in the water. The more photosynthesis, the more oxygen in the water. So the reduction of light by suspended solids causes a reduction of photosynthesis, as I just said. It can also cause issues for animals that rely on sight to catch food. So if you're looking to hunt a fish or something, then you can't see food. The way we measure it, there's two ways, and we'll talk about them in a moment. So it can indicate soil erosion within the catchment. So that might be from logging. Maybe you've cleared an area of forest and now there's more turbidity in the streams because the dirt has washed away into the stream. So the EPA ensures turbidity is measured and monitored. It's measured in NTUs or nephelometric turbidity units. We'll stick with NTUs using a nephelometer, which is a great piece of equipment, good name. Or we can use a Secchi disc, which is the Secchi disc is shown there in the image, and you just basically record how many meters you can see the Secchi disc for. That's useful in deeper water if you can go out on the water. Whereas we can use other things like a turbidity tube as well. Turbidity tube, you're basically looking to see if you can see something through a tube. We have one in school. Turbidity varies naturally in water bodies over time, like after heavy rain, for example, there's going to be more turbidity. If you go down to the Mitchell River at the moment, you'll see it's milky and murky after all the rain we're having. Here it says fish native to Australia have adapted to high turbidity levels in a lot of our waterways. So you think of the Murray River is naturally murky, and so are a lot of our other waterways. It's because they're long, there's lots of dry soil, and when we do rain, it washes the fine particles into these rivers. All right, the next thing I'm going to look at is light intensity, which we can measure. It's the measure of the amount of sunlight reaching a surface. So a decrease in light intensity reduces the rate of photosynthesis, reducing the growth and affecting animals' food and habitat. It's very, very linked to turbidity, and you can measure it kind of the same way with a light probe, which is a data logger, or a Secchi disc again. As I said, it's linked to turbidity levels. The more turbidity, the less light intensity. So it can be measured in terrestrial environments as well, as I've got the picture of a rainforest here, to indicate the different layers of the community. We talked about the different layers of a rainforest, for example. The next physical or chemical environmental indicator we could use is pH. pH indirectly affects biological processes, the rates of chemical reactions and the toxicity of substances. It affects a whole range of things, just how they work and whether they work as well. So pH is measured on a logarithmic scale. So what that means is that it's kind of like an earthquake, where the difference between a level 4 earthquake and a level 5 earthquake is much, much, much less than the difference between a level 8 earthquake and a level 9 earthquake. So it increases like, let's say, 1, 10, 100, 1,000, 100,000 and so on. So it goes up on that exponential kind of curve. So here it says a single unit of change in pH indicates a tenfold change in the environment being measured. So if you go from 7 to 8 pH, it's becoming a basic, so the opposite of acidic, but from 8 to 9 is becoming 10 times more than that first initial increase. I hope that makes sense. The Australian Water Quality Guidelines for Fresh Water recommends that any change more than half a pH unit from the natural maximum should be investigated. So anytime there's a variation more than 0.5 units, then it should be investigated. And here, freshwater has a range of usually between 6.5 to 8.2. 7, remember, is the middle, and when you go down, it gets acidic, and when you go up, it gets basic. So 7 is the middle, and we go down to 6.5 and up to 8.2. So freshwater is usually just more on that alkaline side. Few species can survive in very high or very low pH levels, and we talked about tolerance range. Every species will have their tolerance range, but they can't survive very high or very low because then it becomes acid, essentially, or like detergent. No one can survive in that. And soil pH can be used to monitor a range of degradation processes, such as soil acidification, soil salinity, sulfate conditions, alkaline soil, but also relationships with soil organisms and plant root diseases. So you can actually measure different diseases based on the pH. So one example of a plant root disease is Phytophthora, which is like this fungus that gets into plant roots and makes the plants collapse. And you can't see it, but you can identify it based on a soil pH test. And here's some pH tolerances. So you can see bacteria can tolerate super acidic, very, very, very acidic water or environment, all the way up to very, very, very basic. The only thing they can't is the most extreme of each side. Whereas algae are much more restricted in any acidic environment, but they can survive in a more basic environment. So you can see they only go 0.5 of the level below 7, which is neutral, but they go 4 units up. Carp and cod they kind of, again, can't tolerate acid or acidic water very well, but they can have a slightly more basic environment. Aquatic snails, again, can only tolerate basic environments. They can, if it's acidic at all, then their shells will dissolve, and so they can't tolerate anything below 7. And the greatest species diversity occurs when you have that neutral range. It means that no species will be affected, or very few species are affected by the pH. Okay, the next one we'll look at is dissolved oxygen. This is the amount of oxygen dissolved within the water. So the level of oxygen within the water, that's dissolved in the water, varies with temperature, salt content, the amount of microorganisms, the exposed area of the surface water, the turbidity level, and the biomass of photosynthetic organisms. So there's a big list there. As water temperature increases, as it gets hotter, then the dissolved oxygen level will decrease. We'll talk about this in a little bit, about the specifics and how each of these interact. But dissolved oxygen is a really key factor in how much life a river or a lake can sustain. Fresh water with a dissolved oxygen of 5 parts per million can support a wide variety of organisms, so 5 parts per million or more. Between 1 and 5, they can support some living things, and anything less than 1 part per million indicate there's probably no life in the water. And we're going to talk about this in a minute, but organic waste released into a body of water can reduce the dissolved oxygen level. This is because aerobic bacteria break down the wastes and consume large quantities of oxygen in the process. Okay? We've already heard about this. It's getting towards that eutrophication process, and we're about to look at this in more detail. But first of all, dissolved oxygen is the amount of oxygen that's dissolved within the water that is able to be used for respiration, that is, for all living things to use to breathe. Okay? And one thing that increases the amount of dissolved oxygen is rapids or riffles, just like this one on the image. You can imagine that a lot of oxygen is being